So we have been looking at when to determine if a group is electron withdrawing or electron donating. For something like this, because it has lone pair of electrons, right, it will be considered to be electron donating. Now, it's activating if it has lone pairs of electrons, okay, with the exception of halogens, and it's deactivating if it has a positive formal charge or if it has a partially positive dipole. That's when you have a deactivating subsequent. Exception will be halogens, okay, which are deactivating, weakly deactivating. Finally, you will have an auto and para when it is activating, or you have an electron donating group. Of course, the only exception to that is halogens. So in this case, you can see that there is you have a lone pair of electrons on the nitrogen, so which can be pumped into the ring, or you can have a situation whereby it's pumped out of the ring. That's why it's a moderate activator or an autopower director. The directing effects of all substituents attached to a ring must be considered when you are looking at an electrophilic aromatic substitution. As you can see here, you have the methyl group, which is an autopower director, and you have the nitro group, which is a meta director. And I told you that this is weak activator, but this is a strong deactivator. So what happens is you have, because the methyl group is stronger than the NO2, the methyl group is a better activator. It will direct the bromine to the auto position, while the nitro group will direct it to the meta position. So you have the synergy here, the synergy of both groups, whereby this is a meta director and this is an auto power director. Of course, the power position is already blocked, so the bromine has to come to the auto position. Now, here you can see that we have a strong activator, the OH group, and we have a weak activator. Both of them are auto power directors, okay? And like I told you, a strong activator always wins, which means that the nitro group is going to come here because the OH group is we have an OH group here. The OH group is stronger, so it's going to bring the NO2 over here. Okay. Now, when you consider these two alkyl groups, okay, we can account for these two products. Of course, this is going to be the major product, and this is going to be minor because of this bulky group here. See, If the nitro group adds to the auto position here, you can see that the positive charge resides on the carbon that is connected to the methyl group. It makes it pretty stable. Now if the nitro group were to add to the auto position to this isopropyl group, then you can see that the positive charge resides on the carbon that is connected to the isopropyl group. And this is pretty stable. See, this is stable. Okay. Alright. So considering sterics, like I told you, this is going to be the major for steric reasons, and this is going to be the minor. This will not occur because it's too sterically encumbered, too sterically hindered. Okay. Now, how would we perform the following transformation? You start out with T-butyl benzene, and you want to make 1 T-butyl 2-bromo benzene. How would that happen? Notice that this is a sterically encumbered arrangement. We know that this T-butyl group is an auto para director. So you can direct the incoming electrophile to the auto position as well as the para position. Okay. But you see in this product, you can see that the para position is blocked. So it's not, it was blocked. So the first thing you want to do in this kind of system is to block the para position. You want to block the para position. So introduce a blocking group at the para position, and then you brominate, and after that you can remove the blocking group. So basically what you can do is to first introduce the block. So that's the blocking group. And then you brominate, and then you remove. So you remove blocking group. Okay. So that's basically how you do it. So a great way to block is to do a sulfonation, which you can carry out with fuming sulfuric acid or concentrated fuming sulfuric acid. You get the benzene sulfonic acid, and then you use dilute sulfuric acid to remove it. So basically that is what is being described here. You block, and then in the second you brominate, and then the third you unblock. So in a block you simply remove that, and that's how the para position is now empty. Don't forget, this has also some reagents for mono-substituted aromatic compounds. If you want to carry out a bromination, you have a chlorination, you have a nitration, you have a sulfonation, you have an alkylation or a Friedrich-Krafts alkylation, you have a Friedrich-Krafts acylation, then you have the Clemmensen reduction, and then you have the oxidation of a side chain, and then you have the allylic bromination. And of course, this is a simple reduction of a nitro group. So these are different things you need to know about the monosubstituted aromatic compounds that can be formed from electrophilic aromatic substitutions. Now, to synthesize di-substituted aromatic compounds, we must carefully analyze the directing groups. For instance, if you want to make 3-nitrobomobenzene, the first thing you want to do is you can introduce the nitro group, which is a meta director, right? And then you can introduce the bromine. Now, if you want to make a 3-chloroaniline, you want to introduce the nitro group, which is a meta director, and then introduce the chlorine, and then you can reduce the nitro group to the amino group, and that's how you get 3-chloroaniline. So the directing effect of each of these substituents is very important here. Now, a meta director will be used to install the two groups. Once one of the groups is subsequently converted to its final form, just like you see here. So, like I told you, you first introduce the nitro group, then you introduce the chlorine, and you do a reduction of the nitro group to an amino group. Now, you can also have a meta director in which you can see a meta director but it's converted to an autopara director. You can have a meta director which is an acyl group converted to an alkyl group, which is an autopara director. Or you can have an autopara director which is a methyl group converted to a meta director which is a carboxylic acid group, or a methyl group which is an autopara director converted to the tribromomethyl group, which is a meta director. So you can convert one meta director to the autopara, or the autopara director to the meta director, whichever you choose. Of course, there are limitations you should be aware of for some electrophilic aromatic substitution reactions. Nitration conditions generally cause a main oxidation, leading to a mixture of undesired products. So it's not easy to nitrate aniline, because you're going to get a mixture of undesired products. First of all, you're going to get protonation of the amino group, which now becomes, previously this was an autopara director, but it will become a meta director, okay, because it has a positive charge on the nitrogen. We said that atoms that bear fully developed positive charges, the atom directly connected to the benzene ring, are mostly meta directors. The other downside you have to be aware of is the fact that Fieldcraft reactions are too slow to be practical when the deactivating group is present on the ring. So if you have a deactivating group on the ring, the reaction will not occur. Even if you have a moderate or a strong deactivator, the reaction will not occur. Now, if we're going to design the synthesis, you can see how we start out with, if you're going to make this, right? First of all, you want to do formation, you want to put an acyl group, and then you reduce the acyl group to the methyl, and then you do a sulfonation, and then you do another alkylation, right? And then you remove the block, right? You remove this block using dilute sulfuric acid, and then you do an oxidation to get your final product.